What's up guys, it's me Sir Ernest and today we're going to calculate the moment of inertia of a solid sphere. So this view is where we have your xy plane along the horizontal and the z-axis will be on the vertical. Here, if you're going to assume that the axis of rotation is the z-axis, that means this z-axis is an axis passing through the center. So this can also be your x-axis or even your y-axis. But for now, let's put it as z-axis. So let's say the radius of the solid sphere is A and the mass is M. And if this is a solid sphere, so this is a three-dimensional problem. So therefore, rho will be equal to mass divided by the volume. And let's assume that this is, for now, a constant. So the total volume, therefore, will be equal to 4/3 pi a cubed. So therefore, the mass would be 4/3 pi a cubed times rho. So the element mass that we're going to use here would be a disk. And that disk is symmetric about your z-axis. So in this view, it would look something like this. So this will be your element. So this volume element dV is a circular disk whose thickness is dz and whose radius is r. And this r is the same r that we're going to use later. So therefore, the volume of this disk would be the area of the disk times the thickness. So the area of this disk would be pi r squared and the thickness is dz. So therefore, dm would be equal to rho pi r squared dz. This r is actually related to A and the distance of this disk from the xy plane. So let's call that z. So this is z. And that is related by Pythagorean theorem. So this is your triangle. This is R, this is A, and this is Z. So R will now be equal to A squared minus Z squared. Now we can consider this solid sphere to be a composite of infinitely many circular disks running from this disk up to this part. So for each infinitesimal disk, the moment of inertia would be equal to 1/2 r squared times dm. So taking note that the moment of inertia for a disk rotated about the z-axis would be equal to 1/2 r squared times m, where r is the radius of the disk. But for an infinitesimal disk, it will be diz. Therefore, the total moment of inertia about the z-axis will just be the sum of all the individual moments of inertia of each of the infinitesimal disks that we defined earlier. So this will now be equal to integral of 1/2 r squared dm. So this will now be equal to integral of 1/2 r squared will be a squared minus z squared. So this is a squared minus z squared times dm, which is rho pi r squared dz. So here the integration will now be along the z-axis, and this will be integrated from negative a all the way to a. Because remember that the radius of the sphere is a. So let's put it here. So this is negative a to a. And simplifying this, we now have 1/2 rho pi times a to the 4th z minus 2/3 a squared z cubed plus z to the 5th over 5 evaluated from negative a to a. And this is now equal to 8 over 15 pi rho a to the 5th. So using the definition of the mass and putting it here, the moment of inertia in terms of the mass and the radius will now be equal to Iz equals 2 over 5 ma squared. So this is the moment of inertia of a circular disk rotated about an axis passing through its center. In this case, it's the z-axis. This is also applicable if the axis of rotation is the x-axis or even the y-axis, as long as it passes through the center of your solid sphere. So that's it. I hope you learned something today. Thank you guys for watching, and I'll see you guys in the next video. Bye-bye.